Hello. Yeah, we are back again. Um, I hate this subject, but I don't have any option. As a student, I have to study. Today, this morning, we'll I will have a quiz. I have to study no matter what, even though I hate this subject. There are three. It's not even three chapters, three topics, but um, nine chapters. Definitely, I will. I cannot study nine of the chapters. I really hate the teacher of this subject. I really hate this lecture. She cannot teach at all. She just give homeworks, and I have three overdue homeworks of this, and it's a project homework that requires two people to do, but the teachers only. I I don't have any partner. The teacher could put me into a three people group in a group, but no, she put me alone. So these three subjects I didn't do it. She better accept my home. So she better accept my project too. Like, yeah, I mean, I hope I can finish it before the exam, and I hope she will accept it. She have to accept it. This is outrageous. Again, I mean, it's my mistake because I didn't attend the classes when the group is shared. When the group is when people make a group, I didn't come to the class. But me alone in the group, that's so. What we are doing here is to study. So I will watch this video. I will only watch one video. This one video contains two chapters, and I will not watch the rest of the chapters. I will just study this and we call it a day. And maybe if I can, maybe I will try to do the project, one of the project. And maybe I will finish it today. I have to finish it today. I will try to finish it today.
All right. Um, so last time we talked about vibrations in solids and how we could um, reconcile some of the experimental observations that were in clear
Oh, forgot to. I will not watch the rest.
contradiction with classical theory, how we could reconcile them by letting in a little bit of quantum mechanics into our description of solids, right? So we looked at Einstein's theory and we looked at Debye's theory, both quantum theories, and both gave us some improved match between what we could see in experiment, like drop in heat capacity, especially at lower temperatures, and what is observed, or what is the theory can predict. Today we are going to look at electrons. Right, electrons live in
Professor Terence.
conductors. They can travel through conductors. They are responsible for, most remarkably, electrical current. And we're going to look a little bit at that today. But also they carry heat. So some of the leftover
Oh,
positive.
let me read it real quick. Models of electrons in solids. Truth theory attempts to understand conduction of electrons in metals using a model analogous to kinetic theory in gases. Deals with free electrons in a metal like molecules of a gas in a box. Alright. Sommerfeld theory combines our understanding of Fermi-Dirac statistics with truth theory in order to understand properties of metals that were previously not explained by truth theory. Deals with free electrons in a box. but now treats them as fermions, not classical particles. To be honest, I mean, why is it if it's a fermions? Is it relevant? What is a fermions? Oh, which one is fermions again? Oh, these is fermions. So what's the difference again? Deals with free electrons in a box, but not treats them as fermions, not classical particles. Okay, okay. So Sommerfeld is better than good theory. As we go further in the course, we will see improvement on these models by considering the crystal structure of solids. We can produce a band theory, which explains which materials are conductors, insulators, and semiconductors, as well as the properties of each type of material. Beyond that, we will investigate interactions between electrons, which give rise to superconductivity and other complex properties.
From heat capacity, we're going to also see how quantum theory of electrons in solids helps us address that. We are going to look at these two models today. One is actually classical still, just treats electrons as a gas, as a classical gas. And the other one, the Sommerfeld theory, is actually treating them as fermionic particles, and so introduces Fermi statistics, and so it is quantum. These theories both have success and still can be applied today, even the classical one, which is profoundly wrong. Some aspects of it are still useful. I use it in my lab to calculate practical things about semiconductors like mobilities. And Sommerfeld theory is even better than that, but they're both actually approximations. One dramatic thing they don't include is the crystal structure of materials. So the fact that these electrons we're going to talk about live in a lattice of nuclei that have their own charges, that interact with electrons, and that also impose periodic potentials, and what that does to the quantum mechanical wave functions of electrons is not treated today. We are going to learn that during the next spiral of this course, and we unravel more and more properties of solids. Okay, Drude theory is a kinetic theory of gases.
Okay, shut up. I will read it first. Drude theory was the first model for electron collisions and conductivity and was based around kinetic theory of gases. We make three assumptions. Electrons have an average scattering time. What is that? Is that like the time needed for an electron to scatter to a random proton? And the probability of scattering within a small time interval. Probability of scattering within a small time interval. dt. Once a scattering event occurs, the electron returns from some momentum p to momentum v equals 0. You mean it stopped? But what happened with the energies? Between scattering events, the electron is spun as free particles to applied electric and magnetic fields. They experience Lorentz force.
For electrons. And so it basically treats electrons as little balls that bounce around. And they bounce and they scatter off of things. Things could be nuclei like is plotted here, but they could also scatter off of each other. The electron-electron scattering. Could scatter off of defects in lattices. Actually, they can even scatter off vibrations of lattices. So they can scatter off of phonons. So there are many, many things that electrons can scatter off, but doesn't matter for this theory because it it doesn't go so deep as to consider these different kinds of scattering. It just says that there is an average scattering time averaged over all electrons. There is a mean time after which electron scatters. So obviously you can scatter faster than that, you can scatter longer than that, but actually the way the theory is written here is probability to scatter in time t will be 1. We'll see later that probability to scatter in time t will be 1. We'll see later that makes maybe a small quantitative difference, but no qualitative difference. So scattering, that's assumption number 1. Assumption number 2 may seem a little weird to you.
Actually, I didn't hear the first one.
Longer than that, but you can mean time, which just so deep as to consider these different kinds of scattering. It just says that there is an average scattering time averaged over all electrons. There is a mean time after which electron scatters. So obviously you can scatter faster than that, you can scatter longer than that, but actually the way the theory is written here is probability to scatter in time t will be 1. We'll see later that makes maybe a small quantitative difference, but no qualitative difference. So scattering, that's assumption number 1. Assumption number 2 may seem a little weird to you, but if you think about it, it's still okay. So assumption number 2 is that after scattering, electron loses all momentum. So this must contradict some fundamental laws. Momentum conservation, for example, doesn't look like that applies here. But actually, if you look at one electron event scattering, that is certainly not correct. But if you average, then on average, you can say that momentum becomes 0. Okay. Now, as long as electrons don't scatter, they behave as just simply charged particles would in electromagnetism. They experience electromagnetism. So they experience electric force and a magnetic force in between the scattering events. So external fields, we put this piece of conductor, this piece of solid, typically a metal, but maybe a semiconductor, into an electric field and magnetic field, and they will just, the electrons will just deflect or accelerate or decelerate under the influence of that force. Okay, so let's go through these assumptions one by one to understand them a little bit better. Scattering time is a very, very useful concept which helps you both conceptualize what happens in complex systems with many, many things happening, and also to write down some numerical.
Let me read it first. This is not assumption of kinetic theory. Unlike in kinetic theory, we don't have a good way of estimating T. There's an electron might scatter of many different things. Here, this is phenomenological
Things about the systems. This is what is meant by scattering time here, is that the electron travels for time tau. After time tau, it encounters something and goes off in a different direction. Like I said, this can be impurities in a lattice. This can be other electrons. This can also be lattice vibrations. It can even be a photon if you're close to the surface where photons penetrate. And so the keyword in this slide is that this is a phenomenological parameter, meaning that we cannot look at a piece of solid and just by knowing where the atoms are, how many impurities there are, what the density of electrons is, tell already right away what the scattering time is going to be. We can guess, but we cannot. There is no formula that would tell us what this time is supposed to be.
Okay, so based on the experiment.
We can, however, deduce this time from other measurements. Like we can measure conductivity, and we could, with some additional measurements, maybe with a whole measurement, deduce the scattering time. And I'll show you how we can do this as we go through the theory. Now, once we have gotten some kind of measure of the scattering time, we could later then guess, compare it to what we have in a solid, how many impurities, if we know how many we have, how many crystalline defects, which are probably scattering centers, how many, what is the likelihood of electron-electron scattering, and we could even learn about these things. For example, we could say, okay, it looks like this scattering time is dominated by impurities in this crystal. Right? So this is a very useful parameter for learning about solids, and Drude theory is the way to do it. It's perfectly fine even up to now, so it's not just a historical artifact that we're learning this. Okay, second assumption is about the one that sounds a little crazy, that after a scattering event, momentum goes to zero.
Another assumption is my assumption. After all, when two things collide, it is seldom the case that one stops. However, we can make the assumption that because things are scattered in all directions, on average, their momentum after the collision is equal to zero. This typically works well as an approximation. But if you hit something, this is not supposed to move, the proton is not supposed to move, hit it, then what happens is you bounce off. So I don't understand this zero momentum thing. Later when we think of the electrons as fermions at low temperature. After all, the states with P equals 0 are always occupied, and electrons can be scattered there.
Now, this is not so crazy when you consider averaging over all scattering events. So if you imagine a million of electrons that all start this way and go this way and then scatter in different directions, then on average, the average momentum after 1 million scattering events will be pretty close to zero.
Okay.
So this is why this is not such a crazy assumption. If we assume something different, I believe it will not fundamentally change the result. This assumption, however, makes the calculation a lot easier. So we could account for all of these possibilities and then average over them later. But if we just assume this from the start, I will show you just on this board how you can derive the rest of Drude theory in just a few slides. Okay? So this, let's use this one, and even though it seems a little unphysical, it is actually all good. All right, and the last
Electrons
one
born
is
as
very
free
natural.
particles to applied electromagnetic fields. This natural extension kinetic theory. Little electrons are stellar particles.
Between scattering events, you experience a force, and actually, in this lecture, we will see what happens if you have an electric force, if you have an electric field in a crystal, and if you have a magnetic field as well. So we'll look at both of these scenarios, and in general, you could have both of these fields present at the same time. All right, so let's derive Drude theory. Pretty much half of it is here, and half of it is in the next slide. We go through the three assumptions and use them all. We're going to look at a time interval between
Consider consider an
t
electron
and t plus dt.
that at
So a
time
very small
t
time interval
has
and
momentum p. At time t plus dt at all,
both. All right, so let's derive
probability dt
Drude theory.
with probability.
Pretty much half of it is here and half of it is in the next slide. We go through the three assumptions and use them all. We're going to look at a time interval between t and t plus dt. So a very small time interval. And the rest of this formula can be understood from the following graph. In this time interval dt, there are two possibilities. Either electron will scatter, and the probability of that is dt divided by tau, which is the scattering time. So either electron will scatter with this probability, or it will not scatter and experience a force.
Histeria 12.
And the probability of that is 1 minus dt divided by tau. Okay? So for each electron, in a moment dt, there are these two possibilities. If we sum up over all electrons and take an average. Then we have basically a sum of these two possibilities. Here, when it scatters, momentum goes to sum of these two possibilities. We have basically a sum of these two possibilities. We have basically a sum of these two possibilities. Here, when it scatters, momentum goes to 0. When it doesn't scatter, momentum changes according to Newton's law. Okay, so this is exactly what is written here. So with the probability of dt by tau, we have momentum going to 0. And with the probability of 1 minus dt by tau, this happens to the momentum. dp dt changes under the influence of force. Or you can write it this way. This is the same thing.
Okay. And
Okay.
you know, maybe I'm
So
not
then,
the smartest, but at least what physics has done to me is it teaches me how to do integrals. Because like I know where came from. It is an integral of dp from from above one is t plus dt, and then the below one is t. You know, this dt goes here. So you integrate it. Yeah, it's awesome. It's awesome actually. But one thing that I think is wrong here is um they forgot to integrate this dt also. You are supposed to integrate. Wait, actually not, because that dt you in you integrate it from t plus dt above and t below. When you integrate that, it will become dt again. Oh my god, that's so smart.
an averaged change
So
in momentum during this interval dt is given by this. With a weight of 1 minus dt divided by t, momentum grows by f.
I'm not sure where this one came from. Combining these two terms and widening them probabilities to give the average leaves. How do you combine these? What are you doing exactly here?
In momentum, an averaged change in momentum during this interval dt is given by this. With a weight of 1 minus dt divided by t, momentum grows by f times dt. And with the probability of dt divided by tau, it goes to 0. So this term is just 0. If we expand these brackets, right, so we just have two brackets here. If we expand these brackets, we're going to have terms that are proportional to dt, and then higher order terms, like, for example, if you multiply f times dt with dt divided by tau, you will have a term proportional to dt squared. That term is infinitesimally small compared to the other terms, so we ignore it. And so if we just leave these terms proportional to dt, we can write down this equation at the bottom in the red frame, which is the equation that tells us how average momentum changes as a function of time. Okay? So there is a term proportional to the force, and there is also this term that is basically tells you that there is a decay to some equilibrium state. Okay. So, for example, if you put the force to 0, then you will see that momentum.
Cobain Fresti baru. Fresti, paduannya nikmat. Tali pancing aneh.
Lempar sel COD ongkir. Bayar ongkir di tempat, nggak bayar kalau telat.
I actually can see it, like, because if you put this into 0, what happens? dp over dt becomes minus p over tau, and just forgot the formula of Euler. If you
decays to 0 after a characteristic time tau. And this is also very reasonable because with a small probability dt by tau, but the system loses momentum. There is a probability to scatter into a p equals 0 state. It's a very small probability, but as time goes by, more and more electrons will end up with p equal to 0. And so this is perhaps an artifact of this model that this current decays, but it is also true that the average momentum will go to 0 for a system of electrons once there are no forces acting on them. So even if there is some non-zero average momentum, after a time they will all electrons will randomize their motion and momentum will go to 0. But in this model, they explicitly lose their momentum. They just becomes equal to 0. Okay. So here is this equation for momentum, and what happens to it. And in fact, we know from experiments, and I'm sure you've done it many times, we know that if you apply a constant field to a conductor, then we get a constant current.
yes.
Right? That's Ohm's law, or this is what happens when you hook up a battery to a resistor. You get a constant current. Whereas here, this equation features.
I hate this material very much. I hate it with all my life. I'm passionate hating this subject.
This term dp by dt, which means that electrons have a possibility to accelerate. Well, in fact, this does not happen, and so that's because there is a solution with dp dt equal to 0. So when dp dt equal to 0, this equation can still give us a solution, and this is the solution that the system takes. So this, when dp dt is equal to 0, the solution is called a steady state solution. So there is no time dependence to the parameter we're trying to find. So for now, it has been momentum. We will convert it into something more measurable in a bit. So a steady state solution to this, you just put this to 0. And this is now, we also plug in the electric field. We'll start by looking at what happens with the electric field. And so a steady state solution is just average momentum of this system is not 0. It is something, and this something is given by elementary charge times this phenomenological parameter.
I hate this. I don't even know why I'm doing this live stream. What is my motivation behind this? Who's gonna watch this video? Yeah, I was gonna watch it. I don't even know. Well, my intention of the live stream is actually, I'm not expecting people to watch it, to be honest. I'm serious. I'm not expecting people to watch it. I don't care even. That's because well, I don't do live stream for people, but for the normal videos, the shorts one and the normal one, it is for public for people. But for the live stream, I'm doing it for myself actually. So I don't really care if people watch this or not, which I think no one. I think no one's watching it.
Third
Oh,
tau
it's not thing. No one's watching it right now. I know it.
that we cannot derive from
At least
microscopic
right
details,
now. I mean
but we
currently
just assume
for now.
uh, to be something, and times the electric field. So
You know what? I will turn off this video capture for now.
a constant force produces a steady momentum, finite momentum state on average for electrons. Now we can rewrite this equation in terms of current, which is something that we can actually measure. We don't really measure the momentum of electrons, we measure current. So the way you do that is you say P is equal to M times V, and the current density is equal to density of electrons times their velocity and times their charge. Okay, so this allows us to express this equation in terms of current density J. And so current density J is proportional to the electric field, just like momentum is proportional to the electric field. This is average momentum. Don't put the brackets, but this is average momentum over all electrons. And there is this proportionality coefficient. Who remembers how this is called? When current density proportional to electric field, conductivity. Right? So this is conductivity. Right? And this is the same formula as you may have seen in another class, I think even physics 2. And this is what comes out of Drude theory. Okay, simple enough, right? Equation of motion, look for steady state solution with a derivative going to 0, and find this solution in terms of conductivity. Now, conductivity is written out again here. What does conductivity depend on? We can see that it depends on the density, electron charge, electron mass. Okay, so if we had some other particles magically in a solid, these things would change. And this phenomenological parameter tau. Now, jumping a little bit ahead, I want to tell you how this formula could potentially be useful, start explaining it to you. Okay, so elementary charge of carriers in all kinds of conductors, metals, semiconductors is always E. That is the absolute value of it.
Diskon sampai dengan 30% sudah tiba di Traveloka Black Friday. Dapatkan promo buy one get one.
So at least the magnitude of charge is always E. There are some exceptions. Sometimes we're dealing with 2E charges, but then this entire theory doesn't apply. And sometimes we have charges, exotic things where charge is 1/3. But for most cases, that is always the case. So that's good. That's one solid part of this formula is this letter E. Pretty much everything else is variable, even the mass. Okay? So we will see that in a solid, mass can be heavier than the mass of an electron. You can imagine electron being slowed down by some other particles that attach to it, and so effectively becoming a heavier particle. You can think about this. Or it can be lighter. It can be 100 times lighter than the mass of an electron, the mass of a carrier in a solid. So this mass is quite variable. So you might be using the same formula for some semiconductor, but you will be plugging in a different mass here. You'll be plugging in a much lighter mass. And in that case, the mass is called the effective mass. In semiconductor, mass might be replaced by an effective mass, and that's denoted by m star. So we will see that hopefully later in the course where this comes from. I can tell you for now that it is beyond Drude theory and beyond Sommerfeld theory. So beyond what we talk about today, it comes from adding crystal structure into the model. Now, okay, but let's suppose this is just the electron mass, or you know the mass for this particular material. It doesn't really change from one chunk of material to the other. Then you can learn, in principle, by measuring conductivity, you can learn this parameter, right? It isn't here. It is in this formula. So you could just extract it from the experiment. Except you also need to know the density. So if we had a way to measure the density of electrons, we could separate from just the conductivity measurement this parameter tau and learn about the mean scattering time or mean scattering length, which is sometimes called the mean free path. We learn about how far electrons travel without scattering if we knew what the density was. And it turns out there is a different measurement we could do that will tell us the density, and it also can be demonstrated using the same Drude theory. But for this, we need to include magnetic fields. Okay? So now we look at the same Drude equation, which connects the average change in momentum with the applied force and the scattering process, scattering time. But now instead of the force, we plug in the full electromagnetic force acting upon an electron, which has the electric term, like before, also has a magnetic term. So this V cross B product is the Lorentz force. The Lorentz force is perpendicular to the direction of travel for the electron. Then the approach is very similar, but the outcoming math is a little bit more complex because of this magnetic field and especially because of this cross product. So we find a steady state solution. We put dp dt equal to 0, and this gives us this equation that connects, again, the steady state momentum to the scattering time and the force. And so we can rewrite, again, this equation in terms of not momentum, but in terms of current density. So using, again, the expression for current density, which has density of electrons times the charge times the average velocity of electrons, we can rewrite this expression in a steady state in terms of J. And so what we have here is, again, a relationship between E, the electric field on the left, and J on the right. But now this is a vector equation that is not so easy to make scalar, right? So if we try to write this equation in terms of something as simple as this, like we were able to do for this simple case without any magnetic field, we're going to have to conclude that this rho is a matrix, is a tensor. Right? And that's because of this J cross B product. Because of the J cross B product, rho must be a tensor. So the situation is a little more complex from the math point of view and also from the conceptual point of view. What does it mean that your resistivity is a tensor? Well, what it means in the 3 dimensions is that resistivity is described by this 3x3 matrix. And the 3x3 matrix has terms like rho xx, rho yy, rho zz, rho yx, rho xy, and so on and so forth. So there are different components to this resistivity. And if we just do the math, just stick with the math, and then we will discuss what it means. If we just do the math and we take this equation and try to write it in terms of this matrix, and so we have to open up this cross product here, we will see that the matrix should look like this. Basically, rho xx, rho xy, so rho xx, rho yy, rho zz terms are all the same and coincide with what we found without any magnetic field. Right? So these are just due to the electric field. This is the Drude formula, 1 divided by conductivity. So rho xx is equal to rho yy is equal to rho zz and is equal to 1 over sigma for B equal to 0. Magnetic field equal to 0. And then these terms that come due to the cross product with magnetic field are off diagonal. And they are terms rho xy and rho yx. Okay? And they are B divided by NE. And the other terms that involve Z are actually 0. And that's because Z is the direction of magnetic field itself. Okay? And the way this has been written out.
Oh no,
All right.
this cannot.
So this is the math. Okay, great. Now instead of one number for resistivity, we have a matrix. There seem to be 2 different values occupying this matrix. Well, 3 if you include 0. What does it mean? Well, it means that you can have Hall effect. Right? Everybody remembers what Hall effect is? Yeah? Yeah, maybe? Okay. Well, Hall effect is very nice, and it can be explained in many different ways, but let's just stick to this matrix explanation because these indices x, x, y, x, y, y can actually be related.
Wait, let's see the example question if there's any. We actually have some example here. Sommerfeld. Oh, it is in Sommerfeld model, not in the Drude. Yeah, it's not Drude. Yep. So, but you know, you might argue, well, we have some question in here, but I don't like the question in here. Uh, 3, 4.
Directly to an experimental setup that you use to measure them. So, for example, if I want to measure rho xx, it means that I'm going to apply electric field in the x direction and measure voltage in the x direction. So the sample becomes three-dimensional platform for plugging leads in different directions. So for example, if you look at the blue leads in the picture, they are hooked up in the x direction. And so I can source a current here, and I can measure voltage here, and this voltage will be Vx. And so I'm going to have Vx equal to rho xx times I x.
Not J.
So this would be a standard electrical measurement. Sometimes this is also called a local measurement.
What am I talking about? It's an Ohm law.
Now, what this local refers to is that you measure voltage along the same path as you measure current. So current, just electrical current that you're sending is flowing in the x direction. You also measure voltage in the x direction. That's called local.
Easy, go. Atasan dan berat.
Now, turns out, what I can also do is I can send the current in the x direction. I can measure voltage in the y direction. So it's
What?
called VH here, but I'm going to call it VY. The board is not good enough for this, but VY is going to be equal to rho XY times IX. So I'm sending current in the x direction, same way as before. I'm measuring voltage in the y direction, and that voltage is not zero.
I don't understand what's happening here. What
And
are you
that's
measuring?
thanks to Hall effect, thanks to these off-diagonal terms in the resistivity matrix. Okay? And so this kind of measurement is called non-local. There are other versions of a non-local measurement, but this is one example of a non-local measurement where current is flowing along the x-axis, voltage is measured along the y-axis. Okay?
What I don't
So you can also
understand is
convince yourself
how you choose the row. Like, what makes you think X comes first and then Y? Why not row YX, for example?
that Hall effect makes sense by thinking about what happens to an individual particle, like this electron here in the picture, traveling along the x. So his average trajectory is along the x, but he experiences a Lorentz force that deflects him to one side of the sample preferentially, and this is why there's a buildup of electrons on one side of the sample, right? This is how you could motivate Hall effect, but this is how you can do it from Drude theory in a very simple way, but you have to introduce this conductivity or resistivity matrix or tensor.
Okay.
Okay. Now, Hall effect has been measured extensively since the end of 19th century, and it's been measured for all kinds of materials. And what is convenient to compare is a Hall coefficient. A Hall coefficient just makes the measurement independent of the magnetic field that has been applied. So magnetic field is always in the z direction in the Hall measurement. But then if you introduce this rho h, the Hall coefficient, so it's rho yx or rho xy, those are the same, divided by b, then it becomes minus 1 divided by ne. Okay. So, it's actually important to keep track of the sign of the Hall coefficient, and so I guess we should stick to the definition that it's rho yx divided by b, and then it has this minus sign here. But if we only cared about the magnitude of the coefficient, we could just take the absolute value, of course. Okay. So you can see why this is such a useful measurement. This coefficient is extremely useful because as long as you are sure that your particles carry charge E each, then it tells you the density. So remember I told you if we knew the density, then we could also calculate tau. And actually in semiconductor physics, we often work with this mobility. Mobility is charge times tau divided by m. And so it's the same knowing tau and knowing mobility. Mobility is something that's you find more often in a paper or in a reference to a particular material. That's because when we quote mobility, then we don't need to worry about which tau we're talking about. Physicists, in the meantime, since Drude theory introduced 10 different versions of tau, which all mean roughly the same scattering time, but then maybe scattering time due to this, scattering time due to that mechanism. But mobility is very convenient. So we could figure out mobility by just measuring conductivity, but we need to know this density. So how do we know the density? We just measure Hall effect. We measure rho yx in addition to rho xx. So from a measurement of rho xx plus rho yx, two measurements, we could tell a lot, really a lot about the material, and this is still used to this day to figure out mobilities and densities and so on. Okay. So this is just to say that this is not a useless thing, Drude theory. Now let's see how this theory does when applied to real materials. Let's have a look at this table here. What this table shows.
All right, I don't understand. I don't care.
And
Knowledge Summerfield theory.
Occupation of quantum.
And then we will do
Side
some
that we'll talk
homework.
about
I
today,
mean,
but the
no,
thermodynamic part
some
will tell you
example of
that
question.
this is your heat capacity. And there is a large discrepancy between the measured beta and this one. Okay. So this brings us to Sommerfeld theory. Sommerfeld theory is a theory where, most importantly, we assume that electrons are fermions. And electrons being fermions
Well, I mean,
means
it
that
is a fermion.
there is only one electron per quantum state, right? And
Oh, interesting.
occupation of quantum states, the average occupation of quantum state, is given by this Fermi-Dirac distribution, which in a cartoon form depicted here, at zero temperature, all the states below a certain energy level are completely occupied. This factor will give you 1. And they're completely empty above that level. So that level is mu, or the chemical potential. In this case, this is not mobility, this is chemical potential at 0 temperature. And this is a thing that is featured here in the Fermi-Dirac distribution. And we are going to also call that Fermi energy. So chemical potential at 0 temperature is the Fermi energy. And so the meaning of it is clear, right? Below Fermi energy, everything is... So for simplicity here, let's...
For simplicity, let's do some question. Actually, doing question, then understanding what actually the equation means is, doing the equation is much, doing the question is much easier. Oh, by the way, if you're not, if you don't believe me, well, the thing is, I have the, what do you call it? The solution manual of the book, so I can just look at the solution manual and learn what's going on. Three and four chapter. All right. So here, for example, my lecturer suggests me to do question 1 and 2 for chapter 3, 1 and 2, which means this one. Okay, seems doable. Now what we are gonna do is to find the solution manual in internet. Or I think, okay, let me hide this for a minute. I think I already have the solution manual. Just need to find it. Yep. Where do I put the solution manual? Where is it? Oxford. It's in... Wait, is it in lead solution? No, in lead solution it's only kit. Wait. I'm sorry if you hear that water sound. I just came back from the toilet. Huh. So, Oxford Solid State Basics. Oxford Solid State Physics Basic Solutions PDF. Yep, it's in PDF. It's in the internet. Where is it? Maybe it's in my WhatsApp? Is it in my WhatsApp? That's fascinating. Where is it? Where did I put it? There you go. Found it. Um, this is the solution, ladies and gentlemen. The solution of the book. Now, what I did is just to see the question for number 1 and 2. This is question number 1. It looks mathematic. Oh, I think the question is to derive the equation itself. That's funny because that's exactly what the video did, right? To derive the equation. But here the our task is to also derive the equation. Look at it. I mean, it's doable. Can do it. And then number two, it's more of it's more practical. Yeah, it's more practical. Now let's see. Let's see question. I mean, let's see for the chapter 4. In chapter 4, it's number 1, 2, 3, and 7. Quite greedy. I hate it. I hate the teacher for giving me that. So that's one. I think also derivation of the formula. Yeah, it's a derivation. Number 2, and then number 3. Let me check the group. What exactly is like the chapter that I needed to learn? Maybe there is oh, we have this PDF that the assistant shared to us, and I think the question of the quizzes will be in here. I think so. Let me open it and see. Oh, it is a good book actually. Like it's all just equation, and there is no nonsense like picture or things. It's straightforward, really straightforward. Then we have Fermi Dirac. Also, not only question, but we also have our answer of it, which is very kind of nice. Oh, this is a solved example. Jesus. I like this. Kind of like this. Yeah, so let's go do all of this. 8, 9, 9 problems. I think 9 problems is enough. And after that, we stop. Like, adios. I don't care. Fuck. Oops, I shouldn't say that. I'm sorry. I wanted to say fuck off. Okay, never mind. Alright. Um, let's actually start. Stop overthinking. Starting now is better than not starting at all. Where do I get that quote? I get it from myself. Right. First question. an electron. Wait, can you see the book? Oh yeah, right. An electron is confined in the ground state of a one-dimensional box. One-dimensional box of width 10 to the power of minus 10. Its energy is 38 electrons. Calculate the energy of the electron in its first excited state. Solution from equation 833. Should I derive it? For electron gas, the electron gas in an infinite square wave potential. I mean, we learned this in quantum physics 1. So I don't need to memorize it. Just um, or just energy of infinite, well, potential. Right. Yeah, it's kind of like this is much better. An electron is confined to the ground state of a one-dimensional box. Energy is calculate the energy of the electron in its first excited state. Okay, so the energy of one is equals to I don't know the mass of the electron. Wait, yeah, actually it's just 4 times 38 electron volt, which is 152 electron volt. Right, number one is easy, but the thing is it worth memorizing? And my answer for that is no. Why would you even want to memorize it? What is it? It's just an energy of the infinite well potential. It's not in the any of the yeah, I think I don't need to memorize it. Okay, number two. So a particle in a box shows that the fractional difference in the energy between adjacent eigenvalues. First of all, what is that? I don't think that's worth doing even. Now this we are talking. Now we are talking. Calculate the magnitude of the Fermi wave vector for that amount of electron confined in a box of volume of that volume. So it's number 3. Calculate the magnitude of the Fermi wave vector, whatever that is. I don't know what is that. 4.2 times 10 to the power of 21 electrons confined in a box of volume 1 centimeter cubic. The equation is from 880. Oh, its wave vector is just a wave number. So we know, okay, so let's write some important formula. Fermi wave vector, whatever that is equals to 2 3p square. Okay. I want to write this one also, electron velocity, because it seems like it's important. Electron velocity at Fermi surface. Also, Fermi temperature also seems important. That's the problem. I'm not stressing. I'm a chill guy. You know that meme where a dog where chill guy. I think I need to watch some. I need to hear something. Much better. You can cut my heart to you from you from you. Baca paling surga kuasa ya Tuhan Yesus Kristus dan Sang Roh Kudus ya Tuhan dan berkata satu kami yang telah mengambil dosa-dosa dan kasih saya dan that's wild. But it's kind of fun. Patulah kau Tuhan, ajarlah aku dan perintah-perintah. Ajarlah aku perintah-perintah. Ajarlah aku perintah. Tianina bersama aku karena engkaulah aku di dalam terang kita berpadu sepanjang berkata sang siang sang sang aku selalu selalu bersama sang dapat kuasa yang yang kembali dari angkasa Asianina aku sada dari itu Aku terus kasihanilah kami, aku sanggup tanpa kasihanilah. Bersyukur padamu atas kemuliaan dan kami selamanya sampai panjang sayang sekarang lagi di dalam ajarlah 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 What's going on with it? No sensitivity. Wait a minute. Is it a consequence of 1 over something? Ng Commodore 42. No, still, still shit. Iya deh. Oh iya benar. I don't understand what you're saying. Ya Tuhan, ampunkanlah kami tanpa dosa, berkatilah Tuhan, hanya dari tidak sampai sekarang kami, karena ulas kasih ya Tuhan, sebagaimana hari kejayaan kami di dalam berbaktilah kau, ajarlah ku berikan Tuhan, ajarlah ku ajarlah ku tempat pengungsian kami, keturunan sampai Tuhan berkata siapa sama silam payahku tersumbat dan di dalam pulihkan lagi cari terus sampai saya Equation 877. Which one is that? That the same equation that we have? Oh yeah. What do we have here? Pressure in silver and pressure of electrons in silver at 0 K. Assuming that it has one free electron per atom. I don't understand. Okay, let's start with number of density of electron. Oh, okay. Ah, what is that? What formula is that? What yeah, what is that? Did you get that? That's disturbing. I think this is a kinetic or something. Kinetic energy? I'll write the equation, but I don't know the name. I don't know the name for it. EF, we have this, and then this, N over V. What is N over V? What is N even? What is V even? Oh, the volume is 1. I think we are losing so much context here. Wait, this one looks familiar. Oh, I don't understand. We can skip that. Let's do this number 6. For a system of non-interacting electrons, show that the probability of finding an electron in a state with energy, what is this, above EF is the same as the probability of finding an electron absent from the state with energy below EF given temperature. What is this? Oh, it's delta E. It's delta. Um, it's delta E. Like it's an addition of small e. Okay, number 6 is it's easy. All right. Sorry. I don't quite understand this Fermi thing. When temperature is above zero, this is the graphic looks like. But what is that? What does it mean? What is this? What is this exactly? In order to investigate distribution of electrons above zero K, oh, I reckon the energy is increasing. Energy of what exactly? The Fermi-Dirac distribution function is used. It gives the probability that an electron has an energy E at the temperature T is and it's given by probability electron has an energy E temperature T is given by. Okay, so based on here, the probability is very very low. But in here, for example, the probability is very very high. So no, how do you say? No. If t equals to zero, then the energy is the energy. But if the temperature is above zero, then the energy is varied. It can be in this part, but the probability is low, but in this can be this part. When energy is more than Fermi energy, then probability is zero. Oh yeah, based on this, right? But if the energy is less than energy Fermi, then it's equals probability is equals to 1. As you can see here. Wow, how can I understand this? I'm so smart. No. So this is the energy. Energy Fermi is the energy when it's like this. When t equals to 0. That's the Fermi energy, basically. Should I draw it? Yeah, I guess. Alright, I understand it. Okay, let's see the question. Uh, so the question is, for a system of non-interacting electrons, show that the probability of finding an electron in a state with energy delta above EF is the same as the probability of finding an electron absent from a state. What do you mean? Oh, you can find the. Oh, oh. Here's the thing. We don't need to find the probability of an electron. We just need to find the probability of energy and see if it's the same at any given temperature. Oh, that's interesting. Well, I mean, I think if you think about it, it's because it's actually very simple and kind of stupid. Look at this. This is the energy Fermi, right? If you add like a little bit of energy, it's around here, right? Same probability. But if you less, a little bit less here, also again, same probability. Because by definition, delta is just a small change above or below. Also in here, in this case, also, well, actually in this one, it's kind of different because if it's below, the delta is below, it has the same probability, but if it's above, then it will be zero, which is a problem. So I think it doesn't work for temperature equals to zero. Okay, now look at this. For this one, yeah, same. So it doesn't work at zero actually, but yes, at any temperature, but not zero. Well, you know what? This is just a mathematics. It's kind of annoying and oh, I think F here is not the probability of energy, but the probability of electron. Let's see. What is F? What is F exactly? It's the probability it's the probability of energy, not probability of electron. But I think it's the same thing if you think about it, no? Aku berkata ya Tuhan kasihan karena kau lama. Wait, how is this one equals to 1 again? It doesn't right, it doesn't equals to 1, right? So it equals to, oh, to yeah, it just says it equals to that. Aku berkata ya Tuhan kasihan aku. No. So, so, what's your name? Forgot about that plus one. Oh no. It's wrong. Show that the probability of finding an electron in a state with energy delta above EF is the same as the probability of finding and not finding an electron from a state with energy. So it's actually different. Oh yeah, I think it makes sense. I mean, thinking about it because, for example, the the probability of finding an electron here is zero, and the probability of not finding the electron here is also zero, right? Because you are supposed to find an electron, but the question is the probability of not finding an electron, which is zero. So it's the same. Well, same in here and same in here also. Okay, so yeah, it makes sense now. Jesus. Oh, Jesus. What? Oh, yeah. Okay, it makes sense. It's just chilly. Bukan belas kasihan dalam mereka yang sama-sama sama kasih diri saya sama pernah putus masih yang pernah putus sekarang pun putus masih 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 Are we getting closer? That's right. I don't know how can we solve this equation, to be honest. Minus, right? One minus, and then it becomes. Oh, it doesn't becomes like that. Not quite. One minus, right? It's one minus one over xp, and then. Uh-huh. Oh, oh, oh. My. Let me graph version. I wrote it. Got it. Oh, oh my god. I wrote it like this. It's kind of stupid actually. I wrote it like this. I wrote it like this. Look at my hand. See, there's a additional plus. In actuality, it's supposed to look like this. Oh my god. Sorry if you don't understand what I mean. Maybe okay. So I put plus one in here. Even in here, I mean I have removed it, but I put plus one in there. There's supposed to be no plus one. So yeah, that was my mistake. So that simplifies a lot of our problem. Like a lot. Berkata ya Tuhan, sianilah karena Kau. Okay. Alright, finish. What else? Should I do number 7 also? I think number 7 is quite hard for the coming quizzes. Alright, so I think that's it for this chapter. I think I have I think I have done quite a lot of problem, and to be honest, I think it's time to we can take a rest. Actually, my schedule is to, after studying solid state, I need to do like one project, but I'm too lazy right now. Maybe after class. No, I mean after school, I will do one project. I promise myself to do um one project of solid state that I haven't finished. There are three in total, and all of them are overdue. So three in total. I will do one today. I will finish one. I will finish one. Um, and also maybe I will finish. Remember my relativistic quantum mechanic. I'll also do that. I mean, not all because there are still a lot, but I will do a little bit of it. So yeah, that's it for today. That's it for today. I will. Now it's 5:22, 5:22 a.m. and my class starts at 8 a.m. So yeah, I have time to lay down and straight straight straighten straighten my back. Right.